Yeah, we started last time talking about the introduction to the course. We talked about the course elements and different ingredients that will be included in the course. What is it that we are going to cover? And then we started with the introduction. I'll just go through slightly some of the, quickly some of the ideas that we talked about. We said that in the book we have like the first 5 chapters are introducing us to the subject, and then from chapter number 6 comes the applications, and the applications are the practical ones that you might be seeing in different places while you are moving, even in the streets. Seeing the PV panels, sometimes on the top of houses, you might see that solar collectors, be it flat plate collectors or evacuated tube collectors. So this kind of applications are at the end is what we need to analyze to see the performance, assess the performance, see how good or how bad they might be performing. But before we do that, we need to understand something about the geometry, how the Earth is related to the sun in terms of geometry, and accordingly, how do the changes of solar radiation can happen day by day throughout the year and hour by hour throughout the day. So, talked about the effective temperature of the sun, even the temperature gradient within the sun from the core up to the surface of the sun, how the density changes within the sun, the distance between the Earth and the sun, that the Earth is rotating in not a circular mode, but an elliptic mode with slight differences between the two radii. Then talking about the solar constant, which is the average solar irradiation which is received at the tip of the atmosphere, and then this value reduces as it gets to the ground because of absorption of some of the energy due to the humidity in the air, or having carbon dioxide which is spreaded in different areas of the world, and even talking about some of it being reflected between the dust particles that are suspended in the air and so on. So the value that reaches to the ground is definitely less than the solar constant, which is estimated in this book as 1,367 watts per meter square. The concept of thermal radiation being looked at as a form of electromagnetic waves which are emitted once a surface temperature increased above 0 Kelvin. And at the end, as engineers, what is it that we are interested in? It's not the absolute value of radiation leaving a surface, but it is the relative value that is exchanged between two surfaces. I have one surface at very high temperature, another surface at a lower temperature. Each one of them is emitting radiation, but it is the net amount of radiation that we are interested in, because this is at the end is the net heat transfer rate, which is falling into the lower temperature surface. It is spread over the electromagnetic spectrum for different frequencies and different wavelengths. The relation between the frequency and the wavelength is an adverse relation, meaning that long wavelength is associated with lower temperature surfaces of lower frequency. High wavelength or bigger wavelength, shorter wavelengths are associated with high frequencies. So it's some sort of an adverse relation, and the relation is basically governed by the speed of light, as we have seen in one of the slides, which is showing here the relation between the frequency and the wavelength. C is the speed of light, which is almost 3 to the 10 to, into 10 to the power of 8 meters per second. Another way to represent the emissive power or the radiation is using Planck constant. So the emissive power or the radiation energy is equal to the Planck constant times the frequency. This is the electromagnetic spectrum and how the thermal radiation is being distributed according to it. So we have different values of the solar spectral irradiation depending on the wavelength. It extends from the short wavelength, in which we have the ultraviolet radiation, to the visible range of light, to the long wavelength radiation, which is basically the infrared radiation. And we have seen a table which is indicating what is the amount of the radiation, or what we call the monochromatic radiation, the thermal radiation at a specific value of the wavelength. Actually, what is given here is not at a specific value of the wavelength, but it is some sort of a subtotal emissive power that is being given, or subtotal irradiation that's being provided for an average value within a range. The 0.25 is somewhere in between, like plus or minus values of the lambda, and this is some sort of an average value, and that's the way it goes in calculations. We have taken an example here where we can calculate the radiation which is coming from the sun, which is lying in the visible sort of light, or looking at the edge of the ultraviolet radiation, the edge of the infrared radiation, and look at how much of the solar energy is falling into the visible range, how much is on the ultraviolet, and how much is lying in the infrared. So we've gone through this example last time. And we said that there's another way that we can look at the table by having the distribution not really governed by what is the wavelength and the corresponding value of G, but we're starting from the fraction of the energy and getting the corresponding values of lambda. So it's some sort of a replot of the information that you have got earlier. The sources of extraterrestrial radiation is another issue that we considered last time, which is talking about, for example, how much is the variation due to the change between the distances between the Earth and the Sun all over the year, and the changes in the value which is for solar radiation, which is falling into the Earth anyway. We have gone through a calculations of, or a formula that calculates the variation of the extraterrestrial radiation incident on a plane normal to the radiation on a certain day of the year. So N here's the number of the day of the year, starting from 1 at January 1st and ending with 365 at December 31. So this value of G of extraterrestrial radiation is a function of the solar constant and the day of, or the day order of the year. The day here is appearing in two parameters. One of them is the N, and the other one is shown in the capital B, which is again a function of day of the year. Then the last thing we ended with last time was looking at some definitions, and I just requested you in your own time that you can look at or go through reading some of these definitions, because these are the tools that we are going to utilize throughout the semester. Starting by the word zenith, which is an imaginary point just above us. It's the opposite direction to the gravitational effect. The gravitational is vertically down, this is vertically up. And it's an imaginary point, as I mentioned, above a particular location. Above means vertical direction opposite to the gravity or gravitational force. The word meridian, خط الطول, is an imaginary line that starts from the North Pole going to the South Pole, with the prime meridian is at Greenwich line. It is somewhere in the UK or England. And this is basically the line 0. And then from there, the numbering starts positive in the east direction and negative in the west direction. We also talked about the air mass, which is representative of the ratio of the mass of the atmosphere through which the beam radiation passes to the mass that it would pass if the sun we're in the zenith angle. When we come to this point here, we are talking about the shortest path where radiation takes place as it's going from the sun to the earth. The shortest path is a relative value, how much this kind of distance is compared to that. Does this distance affect the radiation? The answer is yes. It's not only the distance, but the mass of the air or the nature of the air that it goes through. The air changes from one location to the other in terms of, for example, for the humidity which is there. Water vapor absorbs part of the energy. So the shortest length here is taken as AM1, and then we are taking some sort of, these are longer distances, and accordingly the values would change. So this is being measured, and roughly speaking, it's been taken as 1 divided by cosine theta z. What is theta z? This is called the zenith angle, and we are going to define this angle as we are moving in. Typical values of the air mass is being given here. 1, if the sun is at the zenith, and 2, if we have an angle of 60, because cosine 60 is basically equal to 0.5, so 1 divided by 0.5 is 2. I was just browsing to find some sort of if somebody is interested to get a little bit to know about the air mass, then I provided like 3 links that would explain the air mass in further detail. So probably if you're interested, you can go through these links. So what I did, I just modified the presentation a little bit, not only in this, adding this slide, but in a few locations, and I posted the updated presentation on Blackboard, and that's what I'm going to do always. I'll try as much as possible to make the presentation available before the class, but I need you to keep monitoring and seeing the changes, because I would do some sort of updates every now and then. To continue with the definitions, here we are having the beam radiation, which is solar radiation falling from the sun without being scattered by the atmosphere. We know that the atmosphere, as we just mentioned, that atmosphere does some effect of scattering due to the dust particles or due to the clouds, so that would prevent the beam radiation from directly falling into the ground. And here we have this kind of classification, beam radiation versus diffuse radiation. Beam radiation is the direct radiation which is falling into the ground. Why are we not using the expression of direct? Because it might confuse between this subscript. If direct, the subscript might be D. So there's direct and diffuse. So just to avoid using 2 words of the same starting letter, which it's just been tried to look at as direct radiation or beam radiation instead of direct. And the diffuse radiation here is the solar radiation, which is received from the sun after being redirected or scattered by the atmosphere. The atmosphere here includes particles that are suspended in the atmosphere, as well as the clouds as well. The total solar radiation, which is falling into a certain surface on the ground or above the ground, basically, or within the atmosphere, it's a combination of those. So part of the solar energy is coming directly from the sun, and part of it is reflected from either clouds or reflected from some of the suspended material. So the summation of them gives the total, or what we call the global radiation. This is some sort of an illustration of that. Beam radiation, this is the sun, and this is a person on the earth. So direct radiation is called beam radiation. Diffuse radiation is when the direct radiation falls into molecules, and the molecules are absorbing part of it, and the rest is being reflected to the person. So the person is receiving a total radiation, the person or any surface in general. Part of it is beam radiation, part is diffuse radiation, and what he is receiving is the summation of both of these, this plus that. Clouds are reflecting some of the radiation, ground is reflecting some of radiation, and atmospheric particles are again scattering or reflecting part of the radiation. So the sources that can result in diffuse radiation are many, and it depends on how the clarity of the sky on the day. So that's something that varies. I wouldn't say from day to day, but even from a minute to a minute or from hour to hour to an hour. This is again radiation which is falling into a glass of a certain building, like say a window. Part of it is coming directly from the sun, which is beam radiation, but part is being diffused because the sun is having direct rays that are reaching to the clouds. Clouds are scattering some of the radiation to fall into the glass. Dust particles can be contributing to that. In addition to the earth, there is beam radiation falling into the earth, and this beam radiation is reflected back again. So the issue of the kind of radiation which is falling on the surface or on a certain person is basically a combination of direct and diffuse radiation.
Doctor?
Picked another uh, figure here that gives us even a quantitative in a quantitative manner how much of the radiation can be falling directly and how much would be it as diffuse. We have solar radiation, which is incident on the outside layer of the atmosphere as 100%. And then part of it, which is reaching the Earth, it's almost roughly 24%. This is some sort of an average value. It's not a typical, it's a typical value, not exact one, but it would just give us an idea of how much is the radiation falling into a surface. This is direct radiation. And then there is something absorbed by the clouds, say it's about 10%. Some of that is being scattered back or being radiated back, and some of it is going to be radiated from the clouds to the earth. Some of that are going to have like some particles that are taking some of the energy, re-emitting part of the energy to the ground and re-emitting part of it back again to the upper layers. So the direct radiation at the end is somewhere about 1/4 of the total radiation falling, and the rest are basically being scattered here and there.
Doctor?
Yes.
If we use a solar in satellite, solar play in satellite, or use it on Earth, how much difference in efficiency can we talk about?
A lot of difference because there's no absorption when you are talking about in the satellites, which means you are talking about outside the atmosphere. So there's no disturbances for the solar radiation. 100% falls into it
Okay.
compared to here. Basically, actually, the satellites and the space shuttles are powered by solar energy. And for these applications, actually, the type of solar PV panels that are being used is quite different from the ones that we are using on the ground here. Why? Because basically they are going for as high efficiency units as possible compared to the ones that we have here. Currently, the dominating technology for the PV panels are silicon based. They are based on silicon. But the ones that are there are basically based on gallium. It's another substance and it offers like twice the efficiency as what we are having currently on the Earth. It is much, much more expensive, but the applications are rather limited. It's just for space shuttles and for satellites and so on. So it is not a substantial area to be used over there compared to the commercial applications we have on the ground.
Doctor?
Yes.
Now the Earth is already surrounded by a magnetic field or electromagnetic field that save us from harmful radiation from the sun. Now in this case, when we put satellite that uses the solar energy, is it also included in this field, or is it's already out so it can absorb
It's
100%?
already out. I mean, it's outside the atmosphere. So accordingly, the satellites, I mean, are receiving some sort of solar radiation coming from the Earth. I would not think, maybe that's something that we need to be looking at, that it would be much affected by a magnetic field, which is which is outside. It would not, or at least it's being accounted for.
Doctor,
Doctor,
Yes.
how much percentage do we lose when we get through the atmosphere and in terms of the radiation?
Maybe when we look at this, it will give you an idea, because we know the solar constant on the ground is something like 1,367 watts per meter square. What we are getting in the ground now, if we are getting a device that can measure how much is the solar flux falling into a surface on the earth, it would measure a value that will not exceed something between 900 to 1,000 watts per meter square. The device that uses, which is used to measure the solar radiation, is what we call a pyranometer. We'll be talking about that in our next class. So when you are talking about or having a pyranometer, the value definitely it will change from 1 hour to the other. Actually, it changes within less than an hour, and the value at noon, which is, or maybe 12 to 1 o'clock, which is the highest, is something, it depends again, is it summer or winter, which day of the week, what is the conditions of the sky, but typically it would not exceed something like 900 to 1,000. The solar constant is 1,367. So what we are getting is something like 70 to 75%, I would say. I hope that answers your question.
Doctor,
Yes.
now if we use a solar panel outside the atmosphere, how would we translate the electricity to the earth? Is it possible?
It's not to translate the electricity to the earth. It is to power these units. You have a satellite that needs to be powered. You have a space shuttle that you need to power it. It needs energy to run itself, but it will not convert the energy to us.
No, I mean some people say to solar to the using power from the sun to survive, we need to put it outside the atmosphere. So if they did this, how would they translate the electricity?
Again, if this is true, on that sense, or looking at this, it would be, again, you are talking about thermal radiation, which is going to be reflected. For example, China last couple of months, they announced that they came up with some sort of an artificial sun. And that includes some sort of a controlled nuclear reactor that can produce a lot of radiation, which is there, but it doesn't have to be outside the atmosphere. What's outside the atmosphere is because it would have the highest value of thermal radiation falling in, which more or less would be reflection from the solar energy. I'm not sure if I get your point as exact, but just send me the source of this information, then we can search for it.
Okay, thank you.
Fine. So now going into the rest of the definitions, the irradiance, which is the rate of radiant energy incident on a certain surface per unit area. The symbol given for the irradiance is capital G, with a subscript that could be beam or diffuse or spectral radiation. So we have G subscript B, means it's a beam irradiance, G subscript D, diffuse irradiance, and so on. Then the irradiation or radiant exposure. Look at the difference between the units, between the irradiance and the irradiation. The irradiance is watt per meter square, so we're talking about a rate of energy per unit time. But the irradiation or the radiant exposure, we are talking about joule per meter square, so we're talking about a total amount of energy, not a rate, which is some sort of an integration of the irradiance over time. So this is the incident energy per unit area on a surface by integrating the irradiance over a specific period of time, usually 1 hour or a day. Then the word insolation, and note again that it is INSO, not INSU, which means the insulation that prevents the energy or reduces the amount of energy falling or transferred from one surface to the other or one location to the other. The insolation is some sort of a solar energy irradiation. So the irradiation is general, but to be specific and talk about solar irradiation, then it is called insolation, and it has the symbol H. It can be used for a radiation of a whole day, which is capital H, or I for a whole hour. Again, these symbols can have subscripts, and the subscripts can be either O, which is radiation over the Earth's atmosphere as extraterrestrial radiation. B and D stands for beam or diffuse. Again, T and N would stand for a tilted plane or a normal. If we don't have any subscripts with it, then it would mean radiation falling in a horizontal plane. Radiosity, you must have been exposed to radiosity in your study of radiation heat transfer in the heat transfer course. Again, the units are watt per meter square, so it's a rate. So it's the rate at which radiant energy leaves a surface by a combination of emission, reflection, and transmission. You know the surface properties, if you remember, the surface properties include the absorptivity, which means that how much is the surface able to absorb energy falling into it and accordingly get heated. Reflectivity, it's a surface property that indicates how much of the falling energy is being reflected away. And then the engineering application would dictate how much of it that you want. If I want to absorb all the energy falling on a surface, I would just make it a black body. So accordingly, all the energy will be absorbed. But if I need to reflect energy as what happens in parabolic trough reflectors, for example, then I need the surface to be very much shiny so that most of the energy falling on the surface will not be absorbed. The surface is opaque, it will not be transmitted, but rather it will be reflected back again. And then the transmissivity is the amount of energy transmitted from the surface. So the combination of reflected and emitted energy from a surface is what we refer to as the radiosity. If you remember, in heat transfer, we use the symbol capital J to reduce or to express the radiosity. The emissive power is the amount of energy leaving a surface because of its temperature. We have a surface at a certain temperature, so it starts to emit radiation. It does not have the reflectivity as a part of it. So this is the rate at which radiation leaves a surface due its temperature. It's just by emission. Any of these terms can apply to any specific wavelength or range, except for the insolation, which is accounted for the solar energy of a certain spectrum. Solar time is the time based on the angular motion of the sun across the sky. And the solar time is not exactly our own time that we see on the watch. There is a relation between them that we are going to see. It does not coincide with the local clock time, as I mentioned, but we should be able to convert the standard time and solar time by using two corrections. One of them is due to the longitude. For example, if you look at my watch here, the time right now is about 9 o'clock almost in the morning. That would be the same as 9 o'clock in the morning for somebody now in Jeddah. So this is local time, but it is not a solar time. The solar time here and there is different because of the difference in longitude. And this is actually why the times of adhan for prayer is different, because it follows the solar time and changes according to the longitude. So there will be some sort of a constant correction due to the difference in longitude. The sun takes 4 minutes for one longitude angle or degree. The second correction is coming from the equation of time that account for the deviation of the orbit on the Earth rate of rotation. The difference between both of these values, the solar time and the standard time, is given by a certain equation. The equation is shown here that the solar time minus the standard time is 4 times the standard meridional longitude minus the local longitude plus E, which is the equation of time. And the value of E is being given here in that equation, 153, Accordingly, based on the day of the year, we can determine the differences between both of them. Time is usually given in hours and minutes, and probably an example where calculating the solar time versus the local time can be given. This is by the equation of time, by the way, which is this equation. Constants, and B is there, where B is equal to n minus 1, 360 over 365. N is the number of the day that starts from 1st of January as number 1, 31st of December as number 365, or the last day of the year. Then this equation E has been plotted versus the day N, and this has been shown here. And here are the months, January, February, March, up to December, and this is the value of E. How does it change? Then, looking at an example, by the way, the author of the book that we have in hand is basically living in Madison in Wisconsin. That's why the example is being given here, so that you may exercise by repeating this example for the time or the solar time here in Dhahran, and that would be an interesting thing to see. So at Madison, Wisconsin, what is the solar time that corresponds to 10:30 in the morning on February 3rd? So to do that, they need to know what is the standard longitude, which is 90 degrees, and the current longitude or the local longitude, which is 89.4. Substitute into the equation that the solar time is the standard time, which is given in the example as 10:30 in the morning, plus 4 into this difference in the longitude plus E. And when it's calculated here, it will give a value of minus 11. So the time is 10:30, but the solar time is 10:19. In the book, the solar time is considered as the standard in our calculations unless otherwise stated.
Doctor,
Yes.
what does it mean if we talk about solar time? When we have solar time 10:19 and the actual time is 10:30.
It's not actual time. It's the time we call it the local time or the local on the clock. The solar time is not a fixed value. It changes according to the day. What's the importance of the solar time? It would be important if we need to indicate how much is the solar radiation falling into a certain surface. Then being able to calculate it hour by hour, and then we can integrate it over the day. But we don't use it, for example, we will not say that the class is starting at certain hour according to the solar time, but we just say that it's going to be based on the local time. So solar time is being utilized only for the sake of indicating what is the solar radiation which is falling into a certain surface.
If the time, doctor, increase, for example, if the actual time is 10:30 and
Yes.
the solar time is 11, for example,
Mhm.
is it going to be better or is it going to be worse?
No, it's not a matter of better and worse. The point here is, why do we need the solar time? We need it to be able to estimate how much is the solar radiation falling into a certain surface. It does not affect us in our daily routines. So that's why I'm saying that it's not a matter of being better or worse. It's a matter of being able to calculate the amount of energy falling by the sun or from the sun at a certain surface. So it's a way to estimate how much energy is falling at a certain time. That's all. But you cannot adjust your watch on a solar time, for example.
Doctor,
Did I answer your question? It's a little bit confusing, but it's the way it's given so that we can express how much energy is given per unit time. That's all.
Doctor,
Yes.
if we use the regular time, how much error would we introduce into our calculations, would that be significant?
The issue is it will be basically a matter of minutes. But the point here is that it is not constant every day. It changes from a day to day because the equation that we have in front of us is a function of which day of the year that we are talking about. So you needed something which is fixed and accordingly to make it, for example, in Saudi Arabia, you have a single local time for the whole kingdom. In the States, they don't have a fixed time. They have different times, different time zones. The different time zones because it is the state is spread over a wide range of longitudes. Maybe I can give you another example. At Saudi Arabia, at our location here in Dammam or in Bahrain, we are using a certain time, but in Emirates, which is not too far, they are using 1 hour ahead, isn't it? Why is that? Because we are following the time in Riyadh, which is the capital. And according to the longitude of Riyadh, the time has been specified. There, the distance between Riyadh and Dubai has extended over certain wavelengths, certain longitudes. So the point is, we are taking some sort of specific values of the longitudes as taken into it. The solar time does not follow this. It actually changes based on the longitude, and that's why the differences in minutes is there. But you cannot do every city is going to have its own time, so that's going to be confusing. So to standardize the issue or to standardize the appointments and so on, so the issue of the local time has been given.
Doctor,
Yes.
the standard longitude, is it always 90 degree?
Again, and it's 90 in Wisconsin, and this value changes from one location to the other. For example, here we are going to have a different value of the longitude based on Riyadh time. Then in Baghdad, you have a different time. In Cairo, they have a different time. In Morocco, in Casablanca, it's a different longitude. And accordingly, the time +3 or -3 or +4 or -4 or -6 as the states compared to the standard meridian at Greenwich is being determined. So these imaginary values start by 0 at Greenwich and they extend according to the longitude in both east and west. So the point again, the solar time here is being considered for a single reason, which is to determine how much is the solar radiation coming from the sun so that we can be able to calculate it as time changes. Here comes another issue, which is the orientation. And the orientation that we see in front of us here, we have a couple of planes. One plane is passing by the equatorial, and another plane, which is the plane, the elliptic plane, in which we have radiation coming from the sun. So the elliptic plane here is representing the direction to the sun, where the axis of rotation for the Earth is having or tilted. There's an angle between this plane of the equatorial to the plane of where the sun is being exposed, and this declination angle is referred to as delta. This change, in addition to the rotation of the Earth, is making the changes of day and night and changes between the seasons. This angle of the two planes which is the declination angle, has a maximum value of 23.45 in summer and winter. We are going to use the expression of summer solstice or winter solstice, where the values are given as 23.45 or -23 and 45. And this value changes when we come to the spring or the autumn, that we refer to as the equinox. So this is the source of the angles that we are going to see in our next slides.
Doctor,
Yes,
does the angle change during the year?
yes, it does. The value of delta changes, and I have this slide, and the next one will show you how the value of delta changes.
Okay.
So here that we are talking about the winter solstice here, the value of delta is minus 23.45. The summer solstice, where the value of delta is equal to 23.45. And here we have the spring, which is the vernal equinox, autumn, which is autumnal equinox, where the values of delta are equal to 0 in these values. So it changes in every day that goes from summer to winter to spring to autumn, and each day would have a different value of delta. How this is happening, you can see that in this. Now, this is the winter solstice where the angle is minus 23.45. This is the sun and this is the earth. And this is the plane of the equatorial, and this is the plane that has the direct rays from the sun falling into the earth. And the angle is shown here. Whereas, and here, because it's the winter, so the northern hemisphere is going to have, you see this length, which is going in the dark, which means that this is the night and this is the day. So we have a shorter days and longer nights. Look at the summer. It's basically the opposite, because here, this length of the northern hemisphere is longer in the white color and shorter in the dark color. So we have longer days and shorter nights. Spring and autumns, you can see here those values of the planes are having a value of delta inclination of 0, and accordingly we are going to have day and night having equal hours, and this occurs exactly in 2 days of the week, the 21st of March and the 21st of September.
Doctor, doesn't it depend also on the place, or where do you measure it? For example,
Exactly. Actually, what I was referring to here basically was this latitude at the Cancer, but it depends here. This location of the Earth is different from this location, from this location, from this location, and so on. So it does different change. I just took one example here just to show that in some places we have longer night compared to the day, but how long it varies for the location. Here we have much longer nights compared to this. Some areas are going to have 24 hours in the darkness, whereas other areas are having 24 hours of the daylight. And that occurs very close to the poles. Even you probably have heard in the news previously, or you read that some places where you have a day for a couple light of the sun for a couple of days and darkness for a couple of days, or more or less. It depends on the location, and the shade here, the gray shows the night, where the white color shows the day. And depending on your location of the Earth, it depends on how long is it. So the answer is yes, it depends on not only on the day of the year, but not only on the hour, but it always depends where you are in. Is it in the hemisphere, in the upper hemisphere or the lower hemisphere, and where exactly is your latitude that's going to determine that. Again, another look at the angle. Look at this. Here we have the changes of the latitude is following this. So the angle phi would start from 0 at the equator. It increases until it reaches to 90 degrees at the North Pole. Whereas the longitude starts from P here and changes, as we said, that the longitudes are lines that are starting from N, North Pole, to the South Pole, and they are imaginary lines that are given here. Greenwich here is our reference, which is a longitude 0, and then plus or minus depending on the different longitudes and the directions. So we have L is The longitude actually in our case will not be using the word L, but we're going to use another expression for the longitude, and phi is the latitude. And here are some more angles that we'll be dealing with a lot in our calculations. This is the equatorial plane, and this is one surface of a solar collector, for example, which is tilted to the horizontal by an angle beta. So beta is some sort of a tilt angle here, or a slope of a certain device. Then this is the energy coming, or the layer, or the beam which is reaching from the sun and reaching on that point on the surface. Then this ray is making an angle with the vertical, with the zenith, that we call the zenith angle. So theta z is the zenith angle, whereas the angle that it makes with the horizontal is alpha s, and alpha s is what we call the solar altitude. The zenith angle and the angle of solar altitude have a summation of 90, which is this 90. One of them is the angle between this ray and the vertical, the zenith. The other is the angle between ray and the horizontal. So this is the zenith angle, and this is the what we refer to as the solar altitude. Then this is the direction of that surface. This is north, south, east, and west. So the difference between the projection of this ray to the ground and the south is what we call gamma S. And gamma S referred to as the solar azimuth angle. So the solar azimuth angle has to do with the location of the sun. The sun is here, and the projection of this ray of the sun to the horizontal is making an angle with the south, which is gamma S, or the solar azimuth. Why I'm saying that? Because this plane might be facing south or tilted from the south. If it is facing south, then it's going to have a surface azimuth of 0. But if it is tilted from the south, then it's making a surface azimuth, which is gamma. So there's gamma S that represents the solar azimuth, but gamma is the azimuth and angle which is being made with the south. So the angles that we see in front of us here and being defined in this small, we can say, legend key is being given here. Solar altitude is alpha S, the angle that the solar ray makes with the horizontal. Solar zenith angle is theta z, which is the angle between the ray coming from the sun and the zenith, or the vertical line. Then we have the solar azimuth. This is the ray of the sun, how much it is directed from the south. And the plane that we are using, the plane here is associated with two angles. One of them is how much is it tilted from the ground. If beta is 0, then this surface is horizontal. And then you would increase the angle depending on the latitude, definitely, when you are talking about applications, with a certain angle beta. And you can rotate it so that it would be facing south. If it is facing south, the value of gamma is 0. If it is directed from the south toward the east or the west, then we have a value of the gamma.
Doctor,
Yes.
is there a limitation in value of gamma S?
Gamma is following the sun. So we'll see that there are values that we can calculate the value of gamma S and see, for example, why are we studying all of these? What's the point of making use of these angles at all? Because the amount of energy which is falling from the sun is dependent on that. The solar energy becomes more if it is directly normal to a certain surface. How to make it normal to a surface? You try to tilt it from the ground and try to change it so that it would face south or east. Why is that? Because we need to make use of as much solar energy falling as possible. So determination of this inclination and direction of the surface is one of the key elements. Why are we looking for these angles and how to make the angles in a way that we are getting the most benefit from the sun? The value of gamma S changes. Yes, it does change based on, it changes through the day because we know that the sun rises from the east and sets at the west. So the value of gamma S is going to change accordingly. Here are the angles. The value of phi, which is the latitude, it starts from north and south of the equator. North is positive, down is negative. So minus 90 could be the south pole, plus 90 could be the north pole, and then anywhere in between. The declination, we talked about the declination already, that changes from minus 23.45 in winter to 23.45 in summer, and the value of delta changes day to day. So the value of delta is going to be a function of which day of the year, isn't it? And we'll see like a couple of correlations that are providing us with the value of delta. Beta is the slope that you make for your solar collector. If the value is 0, then it is horizontal. If it's 90, it's vertical. And if it's more than 90, then it will be facing the ground, which is definitely you will not see, practically speaking. And when you are putting a solar collector, you need it to face the sun, not facing the earth. Surface azimuth angle, this is the deviation of the projection of a horizontal plane with the south. The value of gamma changes from minus 180 to 180 so that it completes the whole round of 360. Then there is something that we call the hour angle, which is the angular displacement of the sun east or west from the local meridian due to the rotation of the earth. A way or an expression for calculating the hour angle is given by here, by this value, which is the 1.15 into the standard time minus 12. Accordingly, we can calculate an hour angle with 0 given at noon, and then minus in the morning, and then pluses in the afternoon. All of these parameters that we see here, or these angles, are going to be utilized in order to establish a relation between them. And as I mentioned, what is the objectives of doing that and exposing to these is being able to determine what is the best location we can put our receivers to get as much energy as possible. Then we have the angle of incidence, which is a function of the previous angles. This is the angle between the beam radiation coming from the sun and the surface that we have in hand. We talked about the zenith angle. We talked about alpha S, which is a solar altitude angle, knowing that there is a relation between these two angles, that both of them sum up to 90 degrees. And we have also seen the solar azimuth angle, which is, again, the angle between the projection of the ray of the sun and the south. Again, I'm showing the value of delta here, which is the inclination between this plane of the equator to the plane representing the solar rays, which is coming from the sun. Here's the first couple of expressions. One expression is given by Cooper for the value of delta. So you can see here delta is being as a function of n. So you can know how much is the inclination for every day of the year accordingly. A more accurate expression is given by this. And again, B is n minus 1, 360 or 365. You can use either one of them. If I don't specify, you can go for the easier one. And normally in our calculations, we use this equation. It's shorter and easier to use compared to the other one. These values of or relations, by the way, are not to be memorized. I'm going to provide you with equations. Normally in quizzes or exams, you are going to have a formula sheet, and the formula sheet can include this kind of angles. So you don't have to memorize the formula, you just need to know how to use it, that's all. So this is here for the calculations of the inclination angle. This is the value of n. Actually, I was teaching a course last semester, which is having these angles n, and because we are more inclined to use the Hijri date. So the value of n and knowing that how many days in January, how many days in February, and so on is not very common to us. So I would urge you to go through this table and being able to determine the value of n yourself. I might be providing a table like this, but calculating n is something that it should be something trivial. For example, 13th of July, then I would calculate January is 31, February is 28, except for a leap year where February is 29. You know what's the leap year? أو السنة الكبيسة.
No, doctor.
It's every 4 years, February is 29. And how we do that, if the number of the year can be divided by 4 without a remainder, then February is 29. And accordingly, you can come up with every 4 years, we have 1 year of 366 days rather than 365. And what's the reason for that? The reason is the Earth rotates around the sun in 365 and quarter days. But there's no something that we cannot say that there's a quarter day. So it has been decided that it's going to be a whole integer, which is repeated every 4 years. So the leap year or Sana al-Kabisa is something, for example, like 2020. Last year, we have 29 days of February. And then 2024, we are going to have 366 days in the year. But other than that, in between, it is 365. So this is the value of n, how the n is going to be calculated. For example, 10th of September, it's going to be 253. Now you can tell me 15th of November, what will be the value of n?
370.
15th of November, it will be 319,
19, I'm sorry.
yes. So this is the way that you can calculate the value of n, which is again, the order of the day within the year. Here comes now some sort of other formula that again definitely should be provided to you. The useful relations, for example, the incident angle can be related to the delta, angle of inclination, phi, and phi represents what? Remember? Let's get back again and try to remind yourself of these angles. Phi here, it is related to the basically the latitude, isn't it? Which goes from 0 at the equator to 90 at the North Pole. And we have a latitude for every city, which is a standard. You just have to Google it and say, for example, what is the latitude and longitude of Dhahran or Riyadh. And basically, that's something that has to do with again, the GPS, which is that we are using to know the locations by having coordinates of a certain place that are representing what is the latitude and the longitude. So back again to the expression of the incident angle, which is being given as a function of the declination, the latitude angle, the inclination of the surface with the horizontal, and we can make use of that. And omega, again, this is what we call the hour angle that we have seen a while ago. So calculating theta can be given as a function of these angles. All you have to do is know where is your location, what is the day of the year, so you can determine the value of delta, what is the inclination or declination, or we can say the inclination of the surface to the horizontal, then you can determine how much is the incident angle. Or this equation can also be given as a function of the zenith angle, the inclination, and solar azimuth and the plane azimuth. So basically the value of theta can be given as function of these or these angles. Actually, those equations are exactly the same, because if you are going to come up with the value of cosine theta z, cosine the zenith angle, and which is basically is equal to sine the value of alpha s, and this is basically is a function of delta and phi. So if you take this cosine theta z and represented here, you are going to get exactly the same equation that you have there. Example, calculate the angle of incidence of beam radiation on a surface located as, again, Wisconsin-Madison, and you can anticipate that maybe you can do it in a homework on a quiz that I can give you a similar expression or similar example asking for your calculations of the angle of incidence here in Dhahran at certain period of time, or Riyadh, or you can exercise it yourself based on the city that you are living in and see how much the angle of incidence can change within the day and how can change over the year. So the example again, calculate the angle of incidence of beam radiation on a surface located at Wisconsin-Madison again at 10:30 in the morning, solar time, on the February 13, if the surface is tilted 45 degrees from the horizontal and pointing 15 degrees west of south. Now let's look at the angles first. When I say that it's tilted 45 degrees from the horizontal, which angle is this? Tilted from the horizontal means we are talking about beta. This is the angle of our collector or our surface, and it has been tilted from the ground at a certain angle. This is beta. What about the 15 degrees west of south? This is gamma.
Gamma.
You have not yet, been acquainted with this, but I would urge you to have another look at it and probably going through a few examples or a few small problems, you'll be able to get it yourself. But that's something that, as I mentioned, we are using these angles are tools so that we would know, when I know what is the value of cosine theta, how much useful is it? Maybe I can do one of two things. I can see what the highest amount of solar radiation which is falling on the ground is expected to be somewhere between 12 and 1. This is known. Before that, it is lower. After that, it is lower. So maybe if I need to put a solar surface to absorb radiation, I would put it normal to the direction of the ray which is coming. So I need to know what is this direction. So it's basically for this. Or I may need to know how this value is changing if I may need to make a tracking surface, which is a surface that changes its direction artificially using a motor so that always it becomes normal to the radiation falling from the sun as the time changes. And when we talk about tracking, you have a single axis tracking so that it follows the changes, for example, with the value of alpha, or it can be a 2-axis tracking, so I can follow the change with alpha and follow the change with gamma as well, so that we try to get as much as solar energy falling into the surface. So that's why this is the importance of knowing these angles and being acquainted with. So the kind of angles that we're going to need here, the value of theta is going to be a function of alpha s, which is, I'll go back to the previous example. I should know what is the value of delta, and delta is a function of the day of the year. The value of phi, the latitude, beta is the inclination, and then gamma is the solar hour. So these are the values that I need to know or to make sure that I have before starting to apply in this example. And when you look at the substitution here, you'll find that we have substituted in the value or the expression of delta to calculate the value of delta. And we're talking about 13 of February. Then January is 31 days plus 13, so n is equal to 24. The hour angle is being calculated as 15 into 12 or the current time minus 12. The current time is 10:30 minus 12 is 1.5 into 15 gets us minus 22.5. And accordingly, value of gamma has been mentioned. The surface that we have is tilted 15 degrees west of south. So the value of gamma is 15. And it is having an inclination with a ground of 45 degrees. So beta is 45. Phi is the latitude, and latitude is given a standard for every city. You may just look at the internet, or you can find it. It should be a value that would be given otherwise. And the latitude of Wisconsin-Madison is 43 north. Accordingly, you are going to substitute here where the angles are given in degrees. And then you can see at 13th of February at 10:30 in the morning, the angle of incidence is 35. So now you can imagine that we need to do this. Why don't you do that as an exercise just right after the class? Google it to see what is the latitude in Dhahran, which will be something like 20, somewhere between 24 and 26, maybe 24.6 or so. And then you can see, for example, for today, the class is going to finish at, say, 9:45, say 10 o'clock. So at 10 o'clock today, what is the value of theta? Please take this as a little exercise, and we can start our next class by seeing what is the value of theta at that time and that location. Or let's do it at that. What will be the value of theta at the start of the class, 8:30 in the morning? And what's the value of theta as the class finishes? Let's take it at about 10 o'clock in the morning. So the value of theta here and there. And let's calculate it for today. And today is what is today, 20th of January?
Yes,
So what's the value of n
20.
for today? N is equal to
20.
20, exactly. So n is equal to 20. And let's talk about the surface, which is have an inclination of 26 degrees. So please take this as some sort of an exercise. Calculate it yourself. What would be the incident angle at 8:30 in the morning? And then what is the incident angle at 10 o'clock in the morning for a surface which is tilted 26 degrees, which is basically the value of beta in Dammam or Dahran? There wouldn't be a difference. And what is the value of theta for today? Let's have these two values of theta, one at 8:30, one at 10 o'clock, and then see the value. And then we can start our next class by looking at these two values.
Doctor,
Yes.
the hour angle W, how can we find it?
The hour angle, you can calculate it as I've shown you the relation between, which is basically it is 15 into the standard time minus 12. Where's that? Oh, sorry, I was going next. I should go the other way, previous. The hour angle is given here as, I'm sure we've gone through the hour angle a while ago in one of the slides, and the value is basically 15 into the time minus minus 12. Where did it go? I'm pretty sure we have just seen it a while ago. Yes, here is it. The hour angle. Omega is 15 into the local time minus 12, or the solar time minus 12. Solar time is for example 10:30. 10:30 minus 12 is 1.5. So omega is equal to, or minus 1.5. Omega is 15 into minus 1.5. So the answer is minus 22.5. So this is the hour angle. Maybe what I did not do so far is checking your attendance. Abdul Hadi, Abu Zaid.
Yes, doctor.
Abdullah, Abu Shaya.
Yes, present, doctor.
Abdurrahman al-Mashhab.
Yes, present, doctor.
Yusuf al-Muhaish. Yusuf. عمار الثوملي.
Yes, doctor.
حسين الوحيد.
Yes.
صالح البليهي.
Yes, doctor.
عبد الله الدوسري. عبد الله. عمر الجهني.
Yes, doctor, here.
عبد العزيز المقثوي.
Yes, doctor, here.
عمر الشمري.
Yes, here.
عبد العزيز الشهري.
Yes, doctor.
ريان الوداعي.
Yes, doctor.
فهد الزهراني.
Yes, doctor.
عبد الرحيم بيما.
Yes, doctor.
نواف الكعبي.
Yes, doctor.
أحمد خواج.
Yes.
ياسر الشيثل.
Yes.
Okay, so I can see that the numbers keep on changing, but this is expected for the first week. All right.
Doctor,
Yes.
now to find the solar time on Khobar or in Dhahran, should we
Yes.
take the standard longitude is equal to 50, which is for Khobar, or 46, which is for KSA?
Actually, you are going to calculate the solar time based on according to the equation that we have calculated. If you know to determine it, then you can get it from here. First, the equation here is it. If you need to calculate, you see that slide?
Yeah, but I mean 90 and 89.4 are not our value.
No, these are for Madison. You have to get the value
Yes.
for the kingdom. You see what's the value for the longitude angle for Riyadh and what is it for Dhahran. And based on that, you can calculate the solar time. So I wanted you to do, actually, I just left it until I see it, how you are going to calculate it next time to see whether you took care of this issue or not. But I'm glad you raised this point of question, that when I say 8:30 in the morning, I'm talking about a local time. So the first thing that you have to do is calculate the solar time at 8:30. And when I say 10 o'clock in the morning, again, I'm talking about a local time. This is the end of the class. But what is the solar time? So it is the solar time that you are going to start. And the difference is here, the standard value is the value of Dhahran, and the local value is the local value here at, sorry, the standard value is the one which is given in Riyadh. This is the standard of the kingdom. And the local value here is the local longitude in Dhahran. Then you are going to substitute in this and calculate what is the solar time. Then take that solar time to calculate the hour angle after this. So it's a good point. I was leaving it so that you can see if you got it, but you already directed the attention of your colleagues into this point. So solar time is the standard that we are using here. Maybe now it's 9:45, so it's probably where we are going to stop at the moment, and then we are going to pick it up from here in our next class. Actually, I'm moving a little bit slowly with this because it's the first time we are introduced to these angles, and we have to make sure that we are dealing with this comfortably before we can move to next topics of the section, inshallah.
Doctor,
Yes, go ahead.
you have free time now?
Yes, now this is it, and thank you for being here today, and then we'll be continuing in our next class, inshallah.